Okay, we're back with our second example about area between curves. This time we have another parabola and another line. Oh wait, it's kind of like what we had before. Oh wait, before it was two parabolas. It's not always parabolas, by the way. Okay, but this one is kind of weird because notice it says x equals 3 plus 2y minus y squared and x plus y equals -1. I know this is not a function and our calculators can't graph this, but Desmos can. So you have an option. That's using Desmos. It works great, and it would graph it and draw this guy on the left. The second option would be to switch your x's and y's on both your functions. In this case, so basically you're graphing the inverses. But if you just switch your x's and y's on both, being very, very careful, notice that these two graphs look basically the same. It's just that one is a reflection across the y equals x line from the other. So you have options. You can, if you see something like this where you're like, but that's not a function, and it makes you uncomfortable, I don't blame you. But you can, so you can just switch x and y. Just be careful. So that works. Okay, that said, I'm going to go through this whole example using this original graph. So our first thing, like before, I'm going to draw a sample rectangle in. So I'm going to draw this guy in. So here's my sample rectangle, just that little strip. And looking at this guy, like this particular location, the right edge is at 3, the left edge is at -3, so the height of this particular sample rectangle is 6. And I can get that long dimension by doing the right minus the left. And if I'm talking about moving right and left, it's like the right x value minus the left x value. So, or blue minus red, however you want to consider it. The skinny dimension of this little rectangle is some little tiny change, in this case vertically, so that's dy. So this dy is going to be our boss. So once again, we're going to consider the area of that sample rectangle. Called dA. And it's going to be the area of the rectangle, which in this case, it's going to be the right x minus the left x times the thickness, which is the dy. So basically, I have the blue minus the red. And like before, just to kind of make it easier to talk about, I am going to take these guys and I'm going to say let x1 equal the 3 plus 2y minus y squared. And I will let x2 equal, I got to solve this guy, x equals -1 minus y. So -1 minus y. So I had to solve that guy for x since it wasn't in like an x equals sort of form. So I have the right, which is the blue minus the left. So I have, sorry about all the clicking I'm about to do, x1 minus the x2. And that is my little strip of my area. And then once again, to get the whole entire area, it is a sum of all these little strips. I could draw in lots and lots of these things and just get my Riemann sum with all those strips of area. I don't have to do it that way though, because I have calculus to work for me instead. Okay. The dy tells me when I'm setting this thing up here, instead of having x, I want that to be in terms of y. So that's the 3 plus 2y minus y squared. And then minus the x2, which is -1 minus y. dy. And I need some bounds. So I can look at my graph in this case, and the dy, our boss, remember the dy is the boss, and so it says look at the y values. Like I have an intersection point here of 0, -1, and I have an intersection here of -5, 4. but the numbers I want are the y values. So I want the -1 and the 4 for my bounds. And then from here I can clean it up a little bit and then integrate it. So my area is going to be the integral from -1 to 4. I'm going to clean this up, being really, really careful with my signs. 3 minus -1, so I have a 4. And then 2y minus -y, so that's minus negative a plus, so that's plus 3y minus y squared dy. Now I can, so I've set this all up, I can integrate it. So I have my area is 4y plus 3 halves y squared minus 1/3 y cubed from -1 to 4. Remember that proper notation with that bar and the bounds afterwards. Okay, and then I can plug in my 4, so my area is going to be 4 times 4 plus 3 halves times 4 squared minus 1/3 times 4 cubed. Be super careful here because there's, with a -1 there, it's so easy to make a mistake in plugging things in. I like putting some square brackets just because it's visually different. And then 4 times -1 plus 3 halves times -1 squared minus 1/3 times -1 cubed. And by the way, this is so weird, but this answer right here, with, even though it's like long and ugly, this is a completely acceptable answer according to College Board. They're totally cool with that. Because once you get to this point, it's an arithmetic question, not a calculus question. That said, if you get your calculator out and you plug things in, you get, I believe, I have to find it, I think it's 20.833. And so it's not a bad idea to do that, because this way, once I know this 20.833, looking back at this and looking at, it's a little hard to see my grid, they're quite light, but looking at this kind of vaguely triangular region, you know, 20 looks pretty reasonable as its area if I were to count those boxes up. So, you know, if I had something that was negative, I would know I screwed up. If I had something that was really like clearly, you know, like a single digit number or just like in the hundreds, I would know I screwed up. So it's always good to just kind of verify when you hit the end, like, does my answer fit the situation? And the 20.833 seems pretty reasonable. And again, you can check all this on your calculator as well.